Okay, just a couple more notes about Monte Carlo integration. Let me jump back to the notes here. All right, so what we're going to do is we're going to change focus and we're going to look at a specific type of Monte Carlo integration where we're trying to do an expectation. So let me just contrast it with what we've done already. What we were doing before was we had some function g and some interval a to b that we wanted to integrate it over. So we found some candidate density f, and we multiplied and divided by that. This looks like an expected value of this ratio. And so what we did was we estimated the integral by just taking the sample mean of those ratios. So in our specific case, g of x was that e to the negative x cubed. We looked at two different candidate densities f. We looked at the uniform on 0 to 2, and we looked at that transform beta on 0 to 2. We found that the transform beta gave us a less variable estimate. Okay, now what we're going to do is we're changing the setting. And what we want to do is we want to consider an expectation. And an expectation by definition is an integration with respect to some function. Here our function of interest is g with respect to some density. And so if I can draw from this density, I don't really need to, the candidate density is basically already given to me by doing this expected value with respect to some random variable x with density f. So let me just look at a specific example. Consider the, what we want to do is we want to estimate the probability that a random normal is greater than 1. So picture the problem. You've got a standard normal curve. 1 is to the right of 0. We want to know the area under the curve to the right of 1. We know that that's going to be smaller than 1/2. But we don't know what it is. And we could, so imagine I asked you to do a, to estimate it via Monte Carlo. What you would probably do is you would draw a whole bunch of standard normals. You would count how many exceeded 1. You divide by the total number that you drew from, and that would be your estimate of the probability. Well, that's exactly what I have written here. I'm going to draw xi's to be standard normals. This indicator function returns 1 if it's true and returns 0 if it's not. So every time xi is greater than 1, this will return a 1. I'm going to sum them up, and I'm going to divide by the total number of draws. This is our sample proportion. Well, we can write that in terms of an expected value. So the probability that z is greater than 1, it would be formally given by this. This is just integrating our standard normal density from 1 up to infinity. I can rewrite that as throwing this indicator function and changing the limit. So before I had to start at 1 and go to infinity. This I'm integrating from negative infinity to infinity, but this indicator function only turns this on when x is greater than 1. So it's the same integral. But now what we have is we've got something that looks like an expected value. Here is our function g of x. We're integrating it with respect to our standard normal density. And so this intuitive thing that you would have done just naturally can be explained, formally explained by Monte Carlo integration. Okay, so let's jump to R again. All right, so here we are. I'm looking at a different script. This is MC Integration Basics. I'm going to look at the lines 8 through 14. I want to find the probability that z is greater than 1. So I'm going to draw a whole bunch of random normals. Here are 100,000 random normals. And then this is just calculating that, that estimated probability. So notice, if I say R1 to 30, here we've got a whole bunch of random draws. Our first one is greater than 1, second one is not, third one is not, fourth one is not. If I say R1 to 30 greater than 1, see that it returns true for this one, false, and then, so 2 of these 30 turned out to be true. So if I take the mean of that, if it's true counts as a 1, false counts as a 0. So this is our indicator function. I've got 1, 2 out of 30. Really, I've got it out of 100,000 because I drew 100,000 of these. So if I take the mean of those zeros and ones, I get my estimated probability to be 0.159. I can get a variance estimate the same way we did before. The variance of our estimate is 1 over n times the variance of our individual guys. And I can get a confidence interval, which is 0.157 to 0.161. Now, the true value, I'm going to put true in quotes, the true value could be obtained from R by taking 1 minus P norm. Notice that our estimate is pretty darn close to what R would spit out. And our confidence interval contains that. In fact, if you do the help file for the normal distribution, P norm is not something that R can do analytically any easier than we can. It can't do that integral. It has to be doing something numerically as well. And if you look at P norm, the way it's calculating P norm is based on this 1993 paper. So even though this number seems kind of magical, I just typed P norm out. R is doing something similar to what we're doing. It's probably a bit more sophisticated than our Monte Carlo integration, but it has to do something like that. The last thing in this does a multivariate normal. If we could look at a standard normal and calculate the probability that both Z1 and Z2 is less than 1. So the picture you should have in your mind is a standard normal looking down. It would have contours that are circular. We want to know if you put a point at 1, 1 and shaded everything to the left and below that, we want to calculate that probability. And so R does it with this PMV norm. It's going to give a value of 0.707, but we can do our same Monte Carlo integration trick. I'm going to draw a whole bunch of random normals. I'm going to count the ones where both the first and the second are less than 1. Oops, I need to run these lines of code. So here is R, and you can see that the first 2 are false. This one is greater than 1. This one's greater than 1. Line 3, both of them are less than 1. Line 4, both of them are less than 1. And so we could again count these, and our estimate is 0.7079, whereas R got 0.7078. So you can see that our estimate came out pretty close. And again, we can get a confidence interval the same way we did before, just by the variance of our estimate is going to be 1 over the variance of these individual guys. Okay, that's all I got for Monte Carlo integration. So this takes place of the lecture for Wednesday, November 29th. And I hope this all goes well. I will see you when I'm back in town.